Okay, let's prove Lemma One on the way to proving this theorem about the general pattern of solutions of any linear system. The summit, what we are attempting to prove. It'll be a long climb. Okay, the theorem, the general form of linear system solutions claims the following. Any linear system solution set is empty or has the following form. A particular solution plus a linear combination of free variables each times a particular vector, where the free variables can range over any values. Okay, that's what we want to prove, that this is the form that any solution takes. It's either zero or it has this form. If it doesn't have free variables, it will have a particular solution. Okay, there are two intermediate steps, two base camps along the way. The first involves homogeneous linear systems. Let's review the definition. A linear equation is homogeneous if it has a constant of zero, so that it can be written as a linear combination equals zero. So the right-hand side constant in a usual equation can be anything. For a homogeneous system, it has to be zero. A linear system is homogeneous if all the equations in the system are homogeneous. Given any non-homogeneous linear system, there's an associated homogeneous system obtained by setting all the constants to zero. Okay, let's do a little warm-up before setting out. So this is our goal, what we're aiming to get to in this video. Lemma One, general form of just the homogeneous system solutions. What is the claim? The claim is for any homogeneous linear system which has m free variables in an echelon form version of the system, there exist m vectors, beta 1, beta 2, up to beta m, such that the solution set of the system is zero plus that linear combination, x1 beta 1 plus x2 beta 2 plus xm beta 1, where the x's can be any real numbers. If m equals zero, that is if there's no free variables, and the solution set only contains the appropriate zero vector. A homogeneous solution system can never have a contradiction in it because it always has the zero solution. Okay, now before starting, let's consider a special case so we can get that out of the way with linear systems with all zero equations. Here's a homogeneous system in the variables x, y, and z with two zero equations. 0 equals 0 and 0 equals 0. Now it's a little bit odd to say, what does it mean to solve this system? What it means is to find the values for x, y, and z such that these equations are true. You can imagine the 0 on the left-hand side is 0 times x plus 0 times y plus 0 times z. And the second equation is 0 times x plus 0 times y plus 0 times z. Then it seems a little bit less counterintuitive. So what it means is to find all the values of those variables which make these equations true. Okay. And also, how does this result match up with the claim of Lemma One? To answer this question about finding all the values, notice that I can use any values for x, y, and z in those equations because they're already true or still true. So basically, any triple of numbers x, y, and z solves this system. Okay, so we seek the solution to the system, and the solution set is, as just mentioned, because any choices will work, this solution set, the vector x, y, z, such that x, y, z can be anything. Now, how does this match up with the lemma? The lemma says we have, well, first of all, there's all three of these variables are free. There's no leading variables because none of the equations have non-zero leading coefficients. So we need three vectors, beta x, beta y, and beta z. And here they are. We can write x, y, z. We can expand it as 1, 0, 0 times x plus 0, 1, 0 times y plus 0, 0, 1 times z. When you multiply the x in, it only appears in the top, the y in the middle, the z in the bottom. You add three vectors together, you get the one on the right. So there's our three vectors. Now, the pattern is the vector for the first variable has a 1 in the first row, for the second variable, 1 in the second row, and for the third, a variable 1 in the third row. Clearly, this pattern generalizes. It is clear that any zero system with m variables has all m variables free, and the m vectors are the vectors with the beta vectors are all zero components except for 1 in the jth row for the vector of the jth variable. And we can expand all the solutions in terms of these vectors. So the result is that zero systems conform to the claim of the lemma. Okay, Let's start out getting to this, proving this first lemma. We can apply Gauss's method to any homogeneous system to find its same solution set echelon form version. Either this version has at least one row, which is not a 0 equals 0 equation, or all the rows are 0 equals 0 equations. We've just seen that all zero systems conform with the lemma. So the only case to consider is the remaining case with at least one non-trivial row. Any 0 equals 0 equations which might still appear will be at the bottom in echelon form and can be disregarded as trivial arithmetic truths. And contradictions can't arise because the zero factor is a solution. Homogeneous linear systems are necessarily consistent. We will use the well-ordering principle to verify the following fact. Each leading variable equals 0 or is a linear combination of free variables. This is what we've been doing when we've solved these systems. We write each leading variable in terms of the free variables being used as parameters. We want to show here that we can do it for any linear system. So consider an arbitrary non-zero row in our system with leading variable xj. So the variables are like x1 to xj minus 1, xj, and then xj plus 1 up to xn, n variables. Now, we don't know which row this is in, but if xj is a leading variable, it's not going to have any of the x1 through xj variables in it because those are going to be in columns to the left of the xj column. Now there could be on the right a linear, it could be 0, but it could be a linear combination of variables xj plus 1 to xn, but those are going to be variables that could only be leading variables in the rows below this equation. So that's going to be important. In echelon form, again, no x1 to xj minus 1 variables from higher rows appear. The linear combination which follows contains only lower row variables, some of which could be leading, some of which could be free. Here's a diagram of the whole system, the m rows of this echelon form. Now, to get a handle on this, if you look at the left, there's a column with a 1, a j, a k, and an m. We're labeling the non-zero rows from the bottom upwards, the way that we work when we solve a linear system. Now, I've only shown 4 leading terms. XM, we don't know which column these are in, but they're going to, but each next row down is going to be to the right of the ones above it. So we have to have the integers, the variables, labels A, B, C, D in increasing sequence. XA has to be less than, A has to be less than B, B has to be less than C, and C has to be less than D. And that's a consequence of echelon form. Now on the first row, we have the leading term, XA, and its coefficient is CM. I've just given a name to it. Then XB is the coefficient CK, XC is the coefficient XJ, and the last row, or the first row here on the bottom, has coefficient constant X1, XD. So this is the general pattern. The first column records the bottom-up labeling. We've given names to the coefficients of the leading terms, and the linear combination of the bottom row only contains, now notice that the linear combination of the bottom row only contains free variables are 0. In other words, what's over here could be 0, but it can only contain free variables because a leading variable would have to be the right of it, and there are no leading variables. This is the bottom non-zero row, so anything below it's 0. So this one we can always solve by, if this is non-zero, subtracting it from both sides, moving it over here, and dividing by the constant C1, and we'll have X sub D equals, so we'll have a leading variable written in terms of free variables. We need to show that for each of the remaining leading variables above it, we can do the same thing. Let's try to establish this with the well-ordering principle. Here's the diagram repeated. Now, to do this, we're going to suppose the claim that is not true. The claim is that we can solve all these equations, the leading variables, and write them in terms of free variables or zeros. Let's suppose the claim isn't true. Then the claim is false for at least one leading variable. Let's say that variable is row K. We're just giving the one that might be false a name, CK, in row K, okay? Now consider the set of all the integer labels of false rows. We know there's at least one, K, and by well ordering, this set has a smallest member. Call that member J. So the row J has the row that has a false statement that's lowest in this pattern. The claim is false for row J, but is true for all lower rows. meaning that we can, for all the lower rows, any leading variables, we can solve for in terms of free variables, which is what I say here. We can solve for the leading variables in the lower rows, they're either 0 or combinations of free variables. And we can replace all the leading variables in row J, in that linear combination for row J, with 0 or combinations of free variables. That means that linear combination we can rewrite as entirely free variables, subtract it from both sides, and divide both sides by Cj to get the following expression. Now, it's supposed to be that we weren't supposed to be able to do this. The claim was false that we couldn't express x sub c in terms of free variables or zeros, and that's what we've done. This is a contradiction with the result that the claim is false for this row. The consequence of the contradiction is the claim must be true for all rows, because if we assume that any of them are false, we get a contradiction. So it says that was arbitrary. It has to be true for all the rows. To review, if the claim fails for any row, then some false row must be the lowest false row by well ordering. Because the system is an echelon form, this row contains no variables from upper rows, and the variables it can contain are either free or can be replaced by free variables, since all the lower rows can be solved. It remains to construct a beta vector for each free variable from those equations. The construction is given on pages 146 to 147. It is a merely description of how the equations found above relating leading variables in terms of free variables can be written together as one vector equation. The goal of this particular presentation is not only to establish the lemma, but to make it understandable why it's true.